The context for this example involves a kid's game, a game for toddlers called Don't Break the Ice. I'm going to abbreviate it as DBI. If you don't know what this game looks like, I linked onto Canvas a 3-minute video that will show you an example of how to play this game. But basically, little plastic ice cube blocks are put in a big plastic frame. There's a bear standing on one of them, and players take turns with little hammers knocking blocks out of the frame, and whoever knocks the bear down loses the game. So the question is, does the person who goes first have an advantage? So in other words, do they win more than 50% of the time? That actually wouldn't be a good thing. So you don't really want the person going first to have an advantage. If that's the case, after people play the game a little bit, they'll figure that out. And then the truth is, it won't be much fun to play the game anymore because everybody will want to go first and they'll argue over it. So the first thing we want to do here when you are doing what's called a significance test is you want to describe the parameter and the hypotheses. So the parameter that we want is a proportion. So this is categorical data. You either win when you go first or you lose when you go first. So let's say that P first is the population proportion of Don't Break the Ice or DBI winners that go first. So that's the truth. And we don't really know what the truth is. But we can write hypotheses about what that truth might be. So if there is no advantage to going first, then we have what's called the null hypothesis. So the null hypothesis with proportions, and we'll see eventually with means, these are always written as equations. So if you have no advantage going first, if there's nothing special going on, that proportion is 50%. So I'll write it as 0.5. So the alternative is, if you do have an advantage when going first, then the proportion that when going first would be greater than 50%. If you have an advantage, that is the alternative hypothesis. And we're looking for evidence of whether or not that might be the case. Well, that evidence has to come from sample data. So I really did randomly assign a number of years ago AP Statistics students into brackets, and we played a total of 156 games of Don't Break the Ice during class. It happened after the AP exam one year. So 86 of the winners had gone first. So notice this is a p hat. This is a sample proportion. So the number of successes is 86 out of a total number of trials of 156. So that sample proportion of success, 86 divided by 156. So that sample proportion, we're going to call it 0.55. So we'll call it 55%. Now notice, the sample proportion is greater than 50%, but that sample proportion comes from just one random sample of 156 trials. Maybe if we had another 156 trials where students were randomly put into brackets, maybe we would get a p hat that was less than 50%. Maybe we would get exactly 50%. You don't know what you're going to get until you actually do the random assignment and play the game. So what's important, though, in order to apply the sampling distribution for a sample proportion to decide if our result gives us evidence of the alternative, we have to make sure. We have to make sure that the conditions for the sampling distribution are met. So those conditions are the randomness, the independence, and the normality condition. So you'll recognize these from confidence intervals. So randomness, the students were randomly assigned to brackets. I have that right up here. So if you don't have randomness, none of these strategies are going to apply. So for independence, 10 times my sample size. So there were 156 trials. So 10 times 156 is 1,560, and that's certainly less than or equal to the number of possible don't break the ice games that we could play. So for normality, n times p and n times 1 minus p, there's something special here. We are about to assume a p-value assumes that the null hypothesis is true. Well, the null hypothesis uses a value of 0.5. So when we check the normality condition, we don't want to use the p-hat that we found in our sample proportion. We want to use the null hypothesis value when we check this condition. So if we take our 156 times 0.5, 156 times 0.5, if the null hypothesis is true, we would expect 78 successes, and that's certainly greater than or equal to 10. And if n times 1 minus p, so that's also 156 times 0.5, 1 minus 0.5 is still 0.5. Again, that's also 78. So what this is saying is, if the null hypothesis is true, we would expect 78 successes and 78 failures. So the expected success and failure counts are plenty large enough to use an approximately normal distribution for our sample proportions. So now that we've written our hypotheses, the null and the alternative hypothesis, and we've checked our conditions, the randomness, the independence, and the normality condition, now we can calculate the test statistic and the p-value. So what you're about to see is the test statistic sounds like a fancy term, and it is a fancy sounding term, but it just represents a z-score. And our p-value is just a probability like we've calculated probabilities in the past. So the logic behind our significance test is to consider how likely is a statistic as or more extreme than the one observed if the null hypothesis is true. So we are trying to decide how likely is a statistic as high or higher than 0.55. That's what we mean by as or more extreme. So by extreme, we mean in this direction, above 50%. So we can write that as a conditional probability. So look, we want to find how likely, so that's a probability, of a statistic. Our statistic is a p-hat, as or more extreme. So that means as large as 0.55 or larger than 0.55 if the null hypothesis is true. So that conditional statement right there, if the null hypothesis is true, that's what we're assuming. Let's act like the null hypothesis is really true. How likely is a sample proportion like this one? Well, this is just a conditional probability, and to calculate this conditional probability, all that we have to do is use this 0.5 as the truth. So that is going to be the mean of our sampling distribution. So to turn this into a z-score, we need to take our sample value of 0.55 and subtract the truth, subtract the mean, and then divide by the standard deviation of the sampling distribution. So that formula for the standard deviation of the sampling distribution for a sample proportion is p times 1 minus p divided by n. Well, our value for p is 0.5. Then we want to do 1 minus 0.5, and we want to divide by our sample size. Our sample size was 156. So we can turn this expression into a z-score. So I'm just going to type it into my calculator in one shot. So here is my sample statistic. I will subtract the null hypothesis value, what I believe the true parameter may be, and then I'll divide by my standard deviation. So that's 0.5 times 0.5 divided by the 156. So that gives me a z-score, I'll call it about 1.25. So this conditional probability is the same as the probability of a z-score that's greater than about 1.25. And that 1.25 right there, that's what we call the test statistic. And the p-value we could find simply using the normal CDF command like we've done for quite some time now. So if I go to second variables, I'll go down to the normal CDF command. So my lower boundary will be the 1.25 and the upper boundary will be 10. I'll highlight paste. And that will give me my p-value, which we'll call that 0.106. So that's my p-value. So, and then last, write our conclusion. So there are really 4 steps in this process. Write your hypotheses. Check your conditions. You need a test statistic and a p-value, and this test statistic and this p-value are based on a 1 proportion z-test. That's what this is called. So it is a 1 proportion test because we're working with 1 proportion. Shocking. It is a z-test because we are using z-scores. Now we can write our conclusion. So this basic strategy is the way that we will write all of our conclusions for all of our significance tests for the rest of the class. So we'll report our p-value. Our p-value is 0.106. So that p-value, you should compare it to your level of significance. This is alpha, or the level of significance. And that's greater than 5%. So this 5% is our boundary for what is likely and unlikely. So p-values that are less than 5% suggest outcomes that are unlikely. P-values that are greater than 5% are suggesting outcomes that are relatively likely. So at 0.106, this is greater than 5%. This is a relatively likely outcome. So in that case, because it's relatively likely, it is relatively likely if the null hypothesis is true. So what that means is we cannot reject the null hypothesis. This is a relatively likely outcome, or you could think of this as this is not unlikely. So we cannot reject the null hypothesis. So there is not, or there is no evidence to suggest that the population proportion of don't break the ice winners that go first is greater than 0.5. So again, the basic idea, this is not unlikely because this p-value is greater than 5%. All of the nots go together. If it is not unlikely, you cannot reject the null hypothesis. So you do not have evidence that the population proportion is greater than 50%. So if the p-value is less than 5%, if this was an unlikely outcome, then all of the results here are positive. So if it is unlikely, then you can reject, and you do have evidence of the alternative hypothesis. So the good news, though, is rather than doing all of this by hand, the last thing I want to show you is you can do a significance test on your calculator. So go to your graphing calculator, press the Stat button, press the right arrow twice to highlight tests, and right here are all of the different tests that we will run, and we won't even use all of these in AP Statistics. So we want to scroll down to the 1 proportion z-test. Oops, I scrolled too far. Forgive me. Go back up. Right there. So 1 prop z-test. When you find that, press enter. So the first thing that you have to do is give the calculator the null hypothesis value. So the null hypothesis value we used was 0.5. So next, you have to tell the calculator how many successes that you had. So in our data, we had 86 successes. N is the number of trials. We had 156 trials. Then the next thing you do here is you specify the direction of the alternative hypothesis. So remember, our alternative hypothesis, we were looking for evidence that the proportion of winners that go first is greater than 0.5. So we wanted to select the greater than alternative. So if you were in a situation where you had a less than alternative, you would select this option. Tomorrow we will talk about when you would select the not equal to alternative. So now we're done. Highlight calculate, and it will give you everything that you need to write down in order to complete this test. So the z-score, 1.28. And again, notice this z-score is slightly different, and that is because the p-hat, the sample proportion, was not rounded. The calculator didn't round it to 0.55, so we get a slightly different result. So we get a slightly different p-value. The p-value the calculator gives you is 0.100, but it's not different enough to change our conclusion. It does give you the sample proportion, and it does give you the sample size that you entered. But the good news is that going forward, it will be enough in order to write down your z-score and write down your p-value and write down the name of the test that you're using. You're not going to have to always do it by hand. I want you to see that we can do it by hand. It's something that we've done in the past, but we can take advantage of the calculator in order to do the heavy lifting for us. So what's important when you use the calculator? Let me review it. This is a 1 proportion z-test. So on your calculator, if you press Stat and go to Tests, you want to scroll down to 1 prop z-test. For 1 proportion z-test, the first thing you enter is the null hypothesis value. So our null hypothesis value was right here, the 0.5. The next thing that you have to enter is the number of successes. So the number of successes we had was 86. The next thing you have to enter is the number of trials. The number of trials we had was 156. Then the next thing you have to do is specify the direction of the alternative. And we were looking for evidence that the proportion of winners that go first is really greater than 0.5. So we had to specify that greater than alternative for the calculator. Then we can highlight calculate and press enter, and it will do the heavy lifting for us. Going forward, then, you'll be able just to write down the name of the test, your z-score, and your p-value. What will be important is that you learn to write this conclusion on your own. You'll see today in your practice questions, you're simply practicing the individual parts of this process. I am going to ask you to try, there is a worksheet where I'm going to ask you to try another question where I'm giving you the chance to fill in the blank. It's actually another question that's based on the game Don't Break the Ice using data that we generated in AP Statistics. Eventually we'll get to the point where you can do all of these things by hand, but at this point, we just want you to be familiar with the process and get used to using your calculator, and in particular, get used to making conclusions by making comparisons to probabilities.